In this example problem, we have car 1 that's initially traveling with a velocity of 25 meters per second in the positive x direction. So we have car 1 at 25 meters per second, and car 2 with a certain mass has an initial velocity of 45 meters per second in the positive y direction. So this is car 2, and this is 45 meters per second. Alright, and we know car 1 has a mass of 3,000 kilograms, car 2 has a mass of 4,500 kilograms. And two cars collide. Now keep in mind the diagram I've just drawn in the lower left is how we do this for vector addition. Technically speaking, car 1 would be coming like this, and car 2 would be coming up like this, so they actually do collide. Alright, after the collision, we're told that car 1 has a velocity of 35 degrees, so we're going to be 35 degrees above the positive x-axis. So this is car 1. And this is 30 meters per second. And we want to know what the magnitude and direction of the velocity of car 2 after the collision is. Alright, so this is a collision, so we're going to use conservation of momentum. It doesn't say elastic, so that's not going to work. They don't stick together, so it's not perfectly inelastic, so it is an inelastic collision. And remember, since this is a glancing collision, because as soon as you see x's and y's in the problem, you know it's a glancing collision. So that's why I've written down an equation for the x direction and an equation for the y direction. So we know the mass of car 1, and we know the initial velocity of car 1 in the x direction is 25 meters per second because it's traveling only in the x direction. And the velocity of car 2 initially in the x is 0 because the car initially is traveling only in the y direction, so none of it's in the x direction. After the collision, we have car 1 of 3,000 kilograms, and we have to split its final velocity into components. So we have v final x and v final y. Since the x component is adjacent to the 35 degrees, we're going to use cosines. We're going to take 30 times the cosine of 35. And then plus the 4,500 kilograms times v2 final. So that's going to be our part of our unknown. So we have to find that x component. And then we're going to fill out our y direction equation. So we have 3,000 kilograms times 0 because initially car 1 is traveling only in the x direction, not in the y. And the opposite is true for the second car. We're going to take its mass of 4,500 kilograms times 45 meters per second because that motion is entirely in the y direction. After the collision, we're going to take the mass of car 1 times the y component of the final velocity. Since 35 is opposite to the y component, we're going to use sine, so sine of 35 plus 4,500 kilograms times our unknown v final in the y direction. So we have our x component of the final velocity of car 2 is 0.284 meters per second, and the y component of car 2 after the collision is 33.5 meters per second. This means that we're going to be in our first quadrant, so we have v final x, v final y. So we're going to use the idea that velocity is equal to velocity x squared plus velocity y squared, and then we take the square root. So that is how I got 33.5 meters per second. And that theta, we're going to use inverse tangent of vy over vx. So we took the inverse tangent of 33.5 divided by 0.284, and that gave us 89.5 degrees north of east. So essentially it's almost traveling directly in the positive y direction.